Okay, we're back, and in this video, sorry, here I am. In this video, we're going to basically do the same thing: how to write electron configurations and how to write orbital diagrams. That's our objective. That's what we're going to do. That's our skill set that we're doing. But the way we're going to do it is we're going to use a periodic table. So this is section 9.7, titled Electron Configurations and the Periodic Table. So the periodic table is actually organized by number of protons, which essentially is the same thing as electrons as far as number goes, right? Because atoms have the same number of protons as they do electrons, unless, of course, if they gain or lose some to become an ion, but that'll always be noted for you so you can know that. But in general, the periodic table is organized with neutral atoms, okay? And because of that, there's some patterns that we can use in the periodic table that'll totally help us make sense of this. And the periodic table is organized in blocks that will easily help you look at a periodic table and know where the electrons are and how they are configured without actually having to write these electron configurations out. But you'll still need to be able to write these and do these. But honestly, using the periodic table is a way better tool to do that than that silly little off-bow diagram that I showed you in the last video. So follow with me along here in the tunnel of doom as I minimize that and head to the, I'll show you this in just a second, some really valuable periodic tables that we're going to look at to help us solve these. But here we are, and the first kind of concept we need to discuss, this is pretty important, is those valence electrons. So what are valence electrons? Valence electrons are going to be the outermost electrons, the ones that are in the outermost principal shell, the ones that are exposed again to other elements or other compounds. Those are the electrons that are going to react because they're on the outermost shell, right? They're the ones that are most vulnerable to reacting, all right? And so basically the principal shell with the highest quantum number is the way to find the valence electrons. Well, if that's the case and you have an electron configuration, remember all of these whole numbers here represent principal quantum numbers. Basically, if you highlight or underline or circle the ones that have the highest number there, okay, like in this case it's 3, don't consider anything with a 2 or 1 or anything less than 3, but anything that has a 3, we want to highlight that. And then count those electrons, and those will be how many valence electrons you have. In this case, we would have 2 there in the 3p orbital. We also have 2 electrons in this 3s orbital, so we have 4 valence electrons. Again, and those are their addresses, 3s orbital and 2 in the 3p orbital. All right, and so that would be for silicon, right? The rest of these electrons are called core electrons, right? They're kind of at the center. They're being shielded. That's why they're called core electrons, because they're in the core. They're being shielded by the fact that you have these valence electrons. Basically, and what that boils down to, guys, is that these are all stable. They're stable because the shells are full. So they're stable. They don't want to go anywhere. It's these valence electrons out here that are not stable because they're on the outside. And in fact, this p orbital here has a occupancy of 6. It can potentially hold 6, and there's only 2 there. So this element here would love to gain 4 electrons, or share 4 electrons. However it can do it, it would love to have 4 electrons come and join the p table, all right, for dinner. All right. So, and all this is related to bonding. I just as a little quick note and a little plug to the next chapter, which since we're doing these side by side, that's why we're doing that. These valence electrons are what participate in bonding. So whether electrons come into these orbitals or they leave these orbitals, or they share with other valence electrons, you're going to get chemical bonding occur through valence electrons. It's valence electrons that participate in chemical bonding, whether that's ionic bonding or covalent bonding. And we're going to draw structures showing electron dots as the dots. And so stay tuned for chapter 10, and it's all related to this too. So valence electrons are super important. Okay. That being said, those valence electrons aren't always going to be at the very end like this. They're not always going to be at the very end. They're the ones with the highest number. So it's important when you're looking at, like, let's say selenium, and you're looking at an electron configuration, that you don't just pick, you see the 4 here and then just highlight all that, because look, there's a 3D there. And if you're wondering still why in the world, like if you're just watching this video because you haven't watched the others, or if you've forgotten and it's been some time, you're going, why is there a 3 before the 4? Or no, why is there a 3 after the 4? I'm sorry. And that's because of the filling, the way that the way it fills. It's just the way it is. Okay, don't try to put a why to answer the why question to it. It all boils down to just stability. Okay, these electrons here in the 4th have higher energy than those. It requires less energy to fill this than it does to start filling that. So the electrons will first want to fill this, because that's obviously what it has to do, and then it'll start filling those. Okay, and then it'll start filling those. It's just the order, the electron filling order. Okay, it's whichever's easiest. They're kind of like, oh, here's a great way to consider it. The last one of my favorite YouTubers, Tyler Do It. You may want to check out his videos on this too if you can, or other science teachers on YouTube that have pretty good tutorials that are animated and such too. He relates it to parking places. So like these orbitals are kind of like parking places, and electrons are going to want to go and park themselves and reside in the parking place that's easiest to get to. That's not always the closest one, right? That's not always the closest one. So just because the parking spot is closer, like distance wise, you may have to climb a hill or drive up and around to get to it. But if a parking place is further away but it's on flat ground, then it's better to do that. Or let's just say you're parking at Walmart. If it takes less energy to walk into Walmart from a further parking spot, you'll walk the distance because it's less energy than trying to fight with people and time and chaos of trying to park closer. So all has to do with energy, and electrons park themselves in places where it requires the least amount of energy. All right. And so that being said, let's go back to, again, just these electron configurations, be able to tell which ones are core electrons and which ones are not. Now, here's a neat figure we're going to look at first. This is a very simplified periodic table, and it shows basically configurations in there, which is kind of neat. And so you know, you can find full-blown periodic tables with electron configurations in them like this. It's real hard to read though, and it's hard to print out. But if you can find one you can zoom in on and stuff like that, it's a nice little, I guess since we're having an open book test, it could be a way for you guys to cheat, and I know that, so I shouldn't have said that, but maybe it'll be a bonus for those of you that actually watched my videos, because they do exist out there. But I'll have other questions I ask you to still make you understand the concept. And in this periodic table where they've done that, they put these electron configurations. The outer electron configurations are shown here. These are the outer electron configurations of the first 18 elements. All right. And so for these first 18 elements, you're not going to have any subshells where we have like some electrons filling a lower energy orbit before you have these. So like 3 is the highest there is. Sorry, I'm drawing a blank. Yeah, boom, here's one in your book actually too that shows you what I was talking about. But this one in your book shows you only the outer configurations, only the valence electrons. So when you're way down here, you might be saying, where's all the rest of the electron configuration? Where's the rest of the electron configuration that leads up to, let's go to gold. Gold has the outer electron configuration 6s1, 5d2. Well, where's all the 1s, 2s, 3p, 4, all 5s, and where are those electrons? They're not shown here because they're not valence electrons. Actually, they're not they're not outer electrons. I gotta be careful how I say that. And when you get to these D block elements here, it actually gets a little bit tricky as far as electron configurations go, and we'll have to go into that sort of on another lecture when we talk about exceptions. But for now, let's kind of ignore some of these ones way down here where that may exist. The periodic table that's up there that we just looked at is very simple because it just considers these 18 here, basically meaning we're not even getting into these D blocks at all. So the periodic table can be organized into blocks. You have your S block. That would be electrons that are in your S orbital. You have your D block, and you have your P block, and you have your F block. Now, basically the way that works is any of the outermost electrons, whatever orbital they are in, last, then that's going to be the block that element's in. Like magnesium, it's in the S block, so you can guarantee that the last orbital you see in its configuration is going to be an S. And there it is. All these are S. Okay. If you look at the P block, all of the elements are going to have P as their very last. You can see that as the very last orbital being represented. And so this one is always going to have D as its very last. Okay, you're always going to see D. And then for the F orbitals, you're always going to see F as the very last orbital that is being filled. And so if you want to know where like let's say sulfur's valence electrons are, well, its valence electrons, since it's in the P block, and it's real easy to know where the blocks are because you just have the first two blue. The transition metals are gonna be your D blocks, and then your this whole right side of the periodic table is your P block, and your lanthanides and actinides, those ones that actually get pulled out. Remember I gave you those bookmarks that these technically go right there, and this periodic table is actually really wide. Those actually fit right there. Those are going to be your F block elements. So it's actually really easy to memorize where the blocks are. And once you do that, I can give you an element like sulfur, and you can immediately know where its outermost electrons are by going all the way. Well, first of all, you know it's in the P block, so its outermost electrons are going to be in the P block, and you can count 4. So you just go over to the left from where you started, and as you add electrons here, you go 1, 2, 3, 4 electrons there. All right, and then 5, and then 6. So all these have 6 in the P, all these have 5 in the P, 4 in the P block, 3 electrons in the P orbital, 2 electrons in the P orbital, and your first electron that shows up in the P orbital would be this column here. And that makes sense too. So if you work your way from the left to the right of the periodic table, here's how it works. Hydrogen has 1 electron. It fits in the 1s1. Okay. Helium has the second electron, and it still needs to go in that 1s orbital, doesn't it? That's why it's still blue. I know it's way over here on the periodic table, but that's because it's like a noble gas. It's unreactive. So as far as family group goes, it fits better in this family group of noble gases as far as its properties go. But technically, as far as like the blocks go and the orbitals go, it's only got 2 electrons, and so it's the 1s. So you're over here in it should be in the S. That's why it's colored blue. But it fits better there as far as properties go. And then the lithium, you add another electron, you're in the second energy level, which starts out as S. And here's your next electron that would go in 2s2. Well, what about if you had another electron? If you had another electron, it would go in the 2p1 orbital, right? And so as far as all of the valence electrons go for boron, they would all be in the second energy level. You'd have 2 of them in the S, and you'd have 1 of them in the P. So you'd have a total of 3 valence electrons. That's why boron has 3 valence electrons, and it would like to lose those 3 electrons. Actually, and sometimes it'll share, and so will carbon share. But like, let's look at fluorine. Here's a perfect example of an element that would love to gain 1 electron. That's because it has 7 valence electrons. It's got 5 in the P block. 1, 2, 3, 4, 5 in the P block. and it's got 2 in the s block. So it's got 2s2, 2p5 for a total of 7 electrons. If it just had one more, it'd have 8, and it would make the octet rule satisfied, and it'd be like neon. So that's why fluorine likes to gain 1 electron. Remember, everything in this column likes to form a -1 charge. Everything in this column likes to form a -2 charge. These elements, well, sometimes -3, most commonly, but then they start to do some sharing, covalent bonds. And then these metals, remember, these all like to lose 1 because there's only 1 valence electron, and there you can see it, 1s1, 2s1. The valence electron for cesium is way out on the 6th energy level, but it's still in an s orbital, and there's only 1 valence electron there, so it's the 6s1. And it would love to lose that valence electron so that all the other electrons for cesium would be filling their orbitals completely. All right, and so what you can do is read the periodic table from left to right, row by row, and you don't have to worry about skipping things, but you do have to remember this, that the where are we going to put that? Okay, this is a long section. We need to do some examples, but there's something very, very important I need to tell you guys, and I'm trying to find out where the book puts it so that you can find it there. Because see, I'd like for you to be able to refer to a periodic table that's like this, all right? But let's do this. If you Google periodic table with electron configurations or periodic table with blocks, how about this? Periodic table with blocks, then hopefully you'll get what I'm trying to tell you right now. Ooh, this one's really nice. No, where was there was one I really wanted. I like this one. Oh, but it's kind of blurry. Forget that then. This one's probably good. No, because it doesn't show the S. I wonder why that's chopped off like that. How about this one? There we go. That one will work. Let me just save this image. This is probably going to be the one I give you guys. I'm going to save it on my desktop. I'll put this one on Google Classroom probably, but you're free to get your own. Oh, cool. So we don't have the elements here. That's okay. We're just trying to show the blocks here. The way you read the periodic table left to right is like this. Let's say we were wanting to pick an element right here. Okay, so right here where my cursor is, I'm in the fourth row, because the rows of the periodic table refer to energy levels. But what I wanted you to tell you was when you're in the D block, you have to subtract 1 from the row you're in. So you see how this is the 5th row technically. This is 1, 2, 3, 4, 5, the 5th row. Okay, the 5th row, or the 5th period. The periodic table is listed by groups or columns. Groups and columns are the same thing, and rows and periods are the same thing. So this is the 5th period or the 5th row, but for the D block, technically that energy level is the 4D, okay? Because remember, it's technically a lower energy level. This is like a subshell. So we're going to fill these first before we go and try to fill the 5P. So you can't count these as valence electrons. And that's what I wanted to get to right now. Oh, so again, just maybe if you have a periodic table like this, what you could do is you could put like -1 for the D blocks, and you could put -2 for the F blocks. So you always remember to subtract 1 or 2 from the row you're in. Like for example, remember, since these technically go right here, then like this last row, the 5F, is technically in the 7th row, but you have to subtract 2, so you make it the 5F, okay? And so the way you fill the orbitals, forget that, again, forget the silly little orbital filling diagram. You just fill it left to right, row by row, like you read a book. So as you add electrons, here we go. We go 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Very happy. Neon, that would be. And then you go to, after the 2p6, you start filling the 3s1, 3s2. Then you start filling the 3p orbitals. So you got 3p1, 2, 3, 4, 5, and 6. Because remember, 2 electrons per shape. Then you move on to the 4th energy level, 4s, which holds 2. Remember, the s orbital holds 2, so this shape holds 2. You got 4s1, 4s2. Well, you keep going, but this time you drop down to 3d. You're in the d block, and so you go 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10, and then back up to 4. P1, 4p2, 4p3. You see what I did there? So you just read it left to right. And so you just pick an element on the periodic table, and if you want to write its electron configuration, just start reading the periodic table left to right and filling the orbitals. So let me, sorry, invading you there with my pictures there. Let me see if there's a better periodic table that shows this. Oh, this is cool because it does show you the periodic table for what it really looks like. You see how the F block, it really fits in right there. It would be way too long, so we have to pull it out to make it actually fit. But that's actually the 7th row. And we subtract 2 for the F block. We subtract 1 when we're in the D block. And, well, let's just do an example. Let's say I wanted to know what, I don't like that periodic table. Let me pick one that doesn't have colors, maybe. Just so you can see how kind of easy this really is, like a black and white periodic table. If I wanted to know what, let's pick bromine here. If I wanted to know what the electron configuration for bromine is, I don't even need to know, like I've already pretty much memorized the blocks. I have the first 2 columns is the S block. The P block is all of this on the right, the big square on the right. The D block is the transition metals in the middle here, and the F block is here. And so if I want to know what bromine's electron configuration is here, then basically what I would do is I would just start from the beginning. 1s1, well, you don't have to write 1s1. You say 1s2. Go ahead and fill it with 2 electrons. So you write 1s2. 2 is a superscript, remember? And then 2s2, 2p6, 3s2. Go ahead and fill all the 3p with 6, and then fill the 4s with 2, and then fill the 3d. This is, remember, 3d, not 4d. Even though we're in the 4th row, this is 3d. And go ahead and fill it. So put 3d10, and then you're going to go to back up to 4, but you're in the p. And you're not going to fill it completely because that would be krypton. You're bromine right here. So you're just going to put 1, 2, 3, 4, 5. 5 electrons. And so remember, so that's 4p with 5 electrons. So you put 4p5. And if you wanted to know how many valence electrons it has, well, just remember it's the one with the highest principal number. So we're in row number 4. So that's the highest principal number. So I count 1, 2. Don't count any of these because those are 3 Ds, not 4 Ds. So I've got the 2 that are in the 4s, and I've got the 5 that are in the 4p. And so that's a total of 5 plus 2, 7. And of course I know that just by looking at the fact that it's in column 17 or column 7a. Right? But, alright, so this stuff is actually really easy, even though it can be overwhelming at times just because there's so many letters and numbers. It can kind of give you a headache, but it really is easy stuff. And I think what we need to do is do some examples. So I'm going to do some examples, but I'm not really prepared in this in this lesson to quite write out examples. So what I'm going to do is just use some examples that are in the book. All right. And so basically, let's look at this example here, 9.5. It says, write an electron configuration for arsenic based on its position in the periodic table. Now, if I asked you to do that, I really wouldn't know at home how you filled that, if you use the periodic table or not. You could use whatever tool you want, the off-bow diagram, the orbital filling diagram, or a periodic table. And if I tell you you can do it in an abbreviated form, then you can. And that's what they've done here. They've noticed that arsenic is right here in the periodic table. This is a good example. I think we have enough to look at. And instead of writing all this stuff way up here, they can just find the noble gas before it. Okay, so you go up a row, scroll over to the noble gas, and that would be argon. So simply just put argon in brackets like this, and then pick up where you left off. So where do we leave off? If we want to say argon represents everything before it, then what comes after argon? So you just like a book, left to right, row to row. So I'm done. I'm all the way to the right here. Now I need to go to the next row, and this is row number 4. And so I'm going to work my way all the way over here to arsenic, but I have to put this stuff down. Okay, I have to start writing this stuff down. So if I'm going to fill the 4s2, so I fill that. Then I'm going to fill the 3d10 completely, and then I'm going to go into the 4 block, but I'm not going to fill it completely. I'm only going to put 3 electrons there, because see, count 1, 2, 3. There's arsenic. Okay. Is there another example we can look at? Yeah, we could look at phosphorus. If you're going to do an abbreviated diagram, which I don't mind you doing, especially if I asked you, I'll ask you to do a lot. Unless I say full diagram, I don't care if you put an abbreviated. Chemists do this. This is how you're going to find them all the time. So I actually want you to be very comfortable with doing the abbreviated forms. But sometimes I'll make you write the full electron configurations out. But if I ask you to do an abbreviated for phosphorus, which is P, you would find it here in the P block. No pun intended. And if you would just find the noble gas that comes before it. Remember, all the noble gases are in the last column. And so our noble gas that comes before phosphorus is, don't go all the way over to the right like this and pick that one, because that's after phosphorus. That noble gas would have more electrons than phosphorus. You want the noble gas that has less electrons than phosphorus. So basically, this writing down neon in brackets is going to pretty much be the same thing as writing 1s2, 2s2, and 2p6. Okay, you won't have to write all that. You can just put neon in brackets. And then continue where I left off. So go down to the next row. We're in row 3, and we're going to work our way all the way to phosphorus and write down what it takes to get there. So obviously I'm filling the S block, so I'm going to put 3, because I'm in the 3rd row, 3s2. So there you have it, 3s2. Now I'm not entering the D block, am I? I'm on top of the D block. So I don't have to put anything there. I just scroll all the way over to the P block, and I will put our count 1, 2, 3. So there's 3 electrons that need to go in this P block in the 3rd row. So 3p3. So you see how it's like an address? This is like an address of where it's at on the periodic table. That's why if you look, oh no, I can just stay here. If you look at this periodic table here, these are addresses on the periodic table here. Okay, 4p4, 4th row, P block, 4 valence electrons. 1, 2, 3, 4 valence electrons. Let's pick another one, 6s1. I'm in the 6th row in the S block with 1 valence electron, so in the 1st. Okay, if I had 2, it'd be barium, and then the address would be 6s2. All right. Where it gets a little tricky is in the D block. These addresses are a little bit off. They can be off. Like for example, you can see that gold says 6s1 5d10. Well, how can this be 5d10 and this also be 5d10? Gold and mercury have both 5d10 at the end. Well, it's because what happened is it before it completely filled the 6s, it went ahead and filled the 5d. It went ahead and filled the 5d because it was so close. It went ahead and did that. It took less energy to do that, and so it does that before it actually fills the 6s2. It always boils down to energy. What takes the less amount of energy? Where does the electron want to park itself? Where it takes the less amount of energy. But to get out and walk into the store. Because remember, electrons are moving, technically. They're energy. Electrons are never still. They're not parked. But the park and place analogy was pretty good of just understanding why electrons fill themselves in these orbitals the way they do. And so let's look at another example. We have... Well, I think I've given you some homework problems. Isn't there another? Yeah, I only gave you like 4 or 5 homework problems on those, so I'll save those. I think we've done enough examples here, because I do want to talk about the explanatory power of the quantum mechanical model. And then the next video we'll talk about how there's trends and sizes. I mean, there's periodic trends in terms of size, ionization energy, and metallic character. But just to wrap up the electron configurations before we move on, there is some explanatory power to these things. And basically, if we go to the address and you look at the very end, the last outer electron configuration orbital, it tells you how many valence electrons are essentially there, right? You can look at all the noble gases and see that they're full. They have their s and p orbitals full. Okay, the alkali metals, they only have 1 electron in that s orbital when it really wants 2, so it's real obvious they're going to want to lose that. And so that's all they're really trying to say here. Now, this is the last thing I wanted to show you. Could you do ions? Absolutely. What would happen if sodium, if this was the electron configuration for sodium, and we said again that it would want to lose that electron, right? What would the electron configuration then look like with that electron not there anymore? We'll just erase it, and it looks like this. It actually looks like neon's electron configuration. So neon and a sodium ion both technically have the same electron configuration, right? Because sodium's trying to be like neon, really. That's why it lost that electron. Okay. Same with magnesium. Magnesium has this electron configuration, but it would really love to lose those 2 electrons. Even though that orbital's full, there's still the 3p orbitals that are technically totally vacant, and so it would be real nice to get down to this 2p orbitals of the two quantum energy level with both the s and p's full, like this, right? And so that's essentially what we'll do, and that's what neon looks like. 6, 7, 8, 9. Yeah, that's what neon looks like. So a magnesium 2+ ion and neon essentially also have the same electron. Oh, look, check this out. A magnesium ion, neon, and a sodium ion, all 3 have the same electron configuration. And then fluorine, a fluoride ion, which comes from fluorine whenever it gains an electron. When fluorine gains an electron there, it'll also have the same electron configuration as a sodium ion, a neon, a magnesium ion, and a fluoride ion all have the same electron configuration. Because it's always nice. Again, that octet rule is what we're after. We're after filling the S and P. The D and the F, because you're having to subtract 1 and subtract 2, when you go across the periodic table, remember you're having to subtract 1 when you're in the D block. So even though it seems like you're in the 4th row, you're really in the 3rd energy level. The D block and the F block, they're kind of like subshells. So the octet rule comes from the fact that you're filling the S block and the P block with the 8 electrons. And we really mostly deal with these kind of elements, especially in organic chemistry. You're dealing with basically carbon, oxygen, hydrogen. So carbon, oxygen, hydrogen, every now and then some, and tons of nitrogen. Yeah, oxygen, nitrogen, carbon, and hydrogen. And then every now and then some bromine or chlorine, and lots of sodiums. But we don't really deal with like these heavier elements and stuff like that. So the octet rule is just hands down awesome rule to remember. All right, hopefully that helps you. Really, the best way to learn this is to do it. To do it and then ask questions. And so please, please, please chime into my Zoom meetings. And even if you miss my Zoom meetings, they're 30 minutes every single day. If you miss those Zoom meetings, just email me and say, can I get a little help? I've helped multiple students so far, even in the evenings, late at night, because they needed help. And I know that it can be 10 minutes versus 45 minutes when you have your teacher's help. So I'm here for you. Please just chime in, email me, and I can respond like that. I've got my phone right next to me, and I'm responding because I know you guys need that support during this time. And so I want to be there for you during those times. And so it doesn't require much to just push a button and get on Zoom, and I can help you with this stuff with my pen and my whiteboard. And I didn't really do any examples like that on these lecture videos. I'm sorry. That probably would have been the best way to teach this, but I wanted to use these periodic tables. I didn't want to really draw on this, and I don't like the whiteboard function on here for like lecture. So but just do them until you get stuck. That's when you're going to learn. When you get stuck and then you get resolve and resolution through that, when you overcome that hurdle of being stuck, then the light bulb goes off and the light bulb goes on, and it makes sense. Okay? And a lot of this may have made sense watching it, but once you go to do it, you're going to find that, it's tricky, and it's easy to get lost in either that diagram or even get lost in that periodic table. But the tools at your disposal become way more efficient when you use them more often. I didn't give you a ton of homework problems because I'm not trying to overload you guys, but make sure you do those yourself and don't just copy them down, and make sure you understand them when you do them. And if you have to redo them, sure, whatever. But I don't want test time to come and you guys be scrambling to get your homework done because you procrastinated and still don't understand how to do it and are trying to rush to do the test, and the school year's over. And then, so anyways, please communicate with me if you need help. That being said, thanks for watching this video. The next videos are going to be about the other different trends in the periodic table based on electron arrangements. Thanks for watching again.